Good morning, Astronomy 1010. Welcome back to what is actually, should be, your third lecture. Because, as some of you may have forgotten, I asked you to watch part 2 of lecture 1 between Wednesday, when I saw you last, and today. And there's very good reasons for me asking you to do this. I'm going to now try to explain them. Unlike a normal semester in which, wait, let's get this on me here. Unlike a normal semester in which there's lots of missing days and makeup days, this particular semester just had one little goofy hang up. We had one missed Monday because of MLK Day. But after that, every single week was intact, except for spring break, where you take out a whole week. And in this class, we're attempting to do a lecture and a lab every Monday, and a lecture and do our homework every Wednesday. That's so that I can help you do your homework. Get a 100 as fast and as quick as possible. Me helping you, okay? Now, in order to keep this simple and understandable, because people are already getting confused, I wanted us to make up for that holiday by having you guys sometime in that empty space watch the second part of this video and do the homework with me. Yes, I am imposing on you, but the return will be that later on, when you're dealing with all of your classes, when we're supposed to have our final lecture on Monday, May 2, we won't have to do that because we will be in sync. And all of my solar system classes, all the sections will be in sync. That means I'll have one set of instructions for everyone. People are already emailing me. People are getting confused. I'm trying to eliminate that. Now, some of you did this, and I thank you. I stan you, as the kids say, okay? Those of you who did not, you owe me something. You have to go and watch. Now, I made a little boo-boo last time. I thought that the lecture and the homework would be contained, but because things are a little different because of scheduling each semester, what I needed you guys to do was watch lecture 1, part 2 here by watching the first hour and a half. And then I needed you to stop and jump to this video, which was queued up to timestamp 137. And I needed you to do homework 1 and submit it. And just so that I can, shame some people here, I want to just go to one of my sections of 1010. And if we go to our grade center, you will notice that, oops, sorry, wrong one. You will notice that lots of people did their homework 1. And if you didn't do that, then you are out of step with the majority. And I want to shame you privately, publicly, whatever it takes. You need to turn this in because you're behind all these other folks here, okay? Now, I was supposed to grade yesterday, and I didn't get it all done because it was Sunday. And what I'm going to do is I'm going to finish the grading today, and that works out for a lot of you because some of you didn't do this, so that gives you a little grace period to get it in today, right? We'll help each other out here. So please, I need to sort of move forward in this lecture because I have lots of cool, complicated, and fun things to teach you. And part of what I'm going to teach you today builds upon that lecture. So if you missed it, you might be feeling a little confused, and I'll see what I can do about that. A note to any night students present, which I doubt there are too many of you, but I will hold an informational section 6 p.m. tonight to talk to you guys. And that's just for the 101, section 101 people. Okay, we're going to be doing lecture 2, part 1, where we're going to learn some stuff about the nighttime sky, some vocabulary terms. We're going to learn how to orient ourselves and how the sky rotates. And then we're going to learn some coordinate systems to describe stars today. And in our lab, we're going to use this celestial sphere to identify some famous constellations and stars. It's a real fun lab. Obviously, wicked cool to do it in person with your own celestial sphere. Sorry, the pandemic is real. It's happening. So we're going to do the best we can over the Zoom here, okay? Keep that guy handy for later. I'm sure I'm going to need it. A note to everyone that I mentioned before the class started, which is you might want to get a head start and you might want to go to Blackboard and you might want to go to your lab tab, and you might want to print out the first 2 pages, right click, open new tab. This is our lab worksheet. You can either print out the first 2 pages, which is all we're going to need, or if you're really desperate, you could take a ruler and a pencil and reproduce this table, table 2, and table 3, and that should cover you, okay? So if you can't print out stuff because you don't have access to a printer, make the table by hand and follow along. Okay, next order of business. How many of you acquired a Casio FX260 solar calculator? Show them up. Hell yeah.
Mine is coming in tomorrow.
Okay. Well, you'll hurt a little bit today, but try to pay close attention, okay? Cole, rip that thing right out of the packaging, or William, sorry, whoever had it in the pack, take it out of the pack. You're not going to want to return that. This is a tool we're going to need. Okay, very proud to see all the video sharers holding that calculator, and thank you very much for sharing video. That's great, Trinity. I like to hear from you, and I understand not everyone has a camera, but for those of you who do have a camera, thank you for sharing. Hello, Nina. Thank you for sharing video with me so that I'm not lonely here. Remember, if no one shares video with me, you're all getting the pre-recordings, and I think some of you like this live experience, so I'm happy to provide that. Okay. In the lecture that you were supposed to watch, Lecture 1, Part 2, it was a pre-recording from a previous semester. I should have gone over a number of critical skills we'll need for today. I should have talked a little bit about Earth's orbit and some vocabulary terms. I should have taught you a skill called the 4 steps of dimensional analysis. That's like one of the most important things I will teach you all semester. That goes beyond astronomy into just like super duper awesome life skills, believe it or not. I should have taught you guys about the astronomical unit. I should have taught you about the small angle formula and angles. Because angles are a really big part of today's lecture, let's do a very quick review on what was in that lecture, just in case you missed it. I don't really need to go over this because you can watch it again, but just for the sake of the people here live, let's see what you've learned. Let's have you impress me and make me feel comfortable. I'm going to draw a picture that represents the situation at hand in the small angle formula. There is an object in your sky. It could be a moon or a planet. It could be the sun. It could be some astronomical object, which is almost always going to be a sphere. That astronomical object has a diameter, a true physical diameter. And the letter that we tend to use for the diameter of a planet or a star, in this class, we're going to use the letter S. And S, of course, you can think of it as standing for size, physical size, or you could think of S as standing for the diameter. And for now, we're going to measure those star or planet diameters in units called kilometers, all right? You are the observer on Earth. This is you, the observer eyeball, and you are looking at the star or the planet. And that planet subtends some angle on your sky. And the symbol that we use for the angular size is the Greek letter theta. And for now, we're going to be measuring angular sizes in degrees, okay? So I'm always specifying you the proper units to use. And the angle relates to the size of the object by its distance. For starters, we will measure the distance between Earth and the object in kilometers. And the message that I had for you last time, if you paid close attention, is that you see angles, not sizes, when you look at astronomical objects. Let's take Mr. Dirty Ping Pong Ball here, okay? Mr. Ping Pong Ball has a true diameter. If I measured it, ping pong ball is roughly 3 centimeters in diameter, but we do not see ping pong ball as 3 centimeters. We see it as an angle. And that's not only true for your eyeball in interaction life, it's also true for cameras and telescopes. You're viewing me through a little web camera, which is kind of like a little mini telescope of sorts. And if I move this close to the camera, it blocks your entire field of view. And as we move farther and farther away, Mr. Ping Pong Ball subtends a smaller and smaller angle. You see angles whether you're looking at something like this eraser in the nearby field of view, or if you look at something on the sky. And as I should have mentioned last time, actually, let's get some slideshow going here. Excuse me, friends. That's what I was forgetting to do. I was forgetting to queue up my slideshow. Okay. Share screen. Boom. And got a couple of pictures to share with you guys to help you understand angular size. Like I said, this is supposed to be review, okay? Function F536. We can talk about angles in two different contexts. I could talk about the angular size of an object like the moon or the sun or a planet. I don't know why they said angular distance. People have a way of doing dumb all the time, right? And this is angular size. Angular distance is very confusing to me. Angular size, okay? We could talk about the, oh, sorry, not angular size. This is angular, now I'm doing it dumb. Look at me go. It's angular separation. That's what I wanted to say. So when I talk about the angular size of the moon, I'm thinking of the moon as a disk on my sky. When I talk about the angular separation between two stars, I'm asking how many degrees on the sky is it between, say, Betelgeuse and Rigel, right? So let's look at a picture here for help. Here we see an observer measuring the angular size of the moon or measuring the angular separation between the two so-called pointer stars of the Big Dipper. Now, whatever weed-smoking artist they hired to be the illustrator clearly didn't fucking understand astronomy, because they're showing the person with their arms bent, which greatly irritates me. Your finger held outstretched subtends roughly 1 degree on the sky. So from where I'm standing, my head on the screen is about 2 degrees, okay? That's the angular size of my head relative on the screen or so, 2 degrees. If your arm is outstretched, your finger subtends 1 degree, a fist is 10 degrees, and if you do thumb to pinky in the hang 10 style, then that's about 25 degrees. And people use their hands as a rough and ready angular measurement tool, okay? It is a curious coincidence that the angular size of the sun and the angular size of the moon are both approximately half a degree on your sky. And that means they subtend half the width of your outstretched finger. So if you hold up your outstretched finger to the moon sometime, you should see it be about half the width of your index finger. I should have also mentioned that that's true whether the moon looks huge or not. The moon illusion is a perceptual effect caused by the fact that you're seeing the moon against a distant horizon with a foreground of cactuses or buildings or trees. And your brain is hardwired to understand that if the moon is half a degree, but past everything you can see on the horizon, that the moon must be a very big object. Your brain knows that, okay? And you can measure its angular size, whether it's a big moon on the horizon or up in the sky, it'll still be half the width of your finger. The moon actually does change its angular size by a tiny amount. And that's because the orbit of the moon is not a perfect circle. For instance, you guys learned a couple of vocabulary terms. The people who I see in my video here, you all watched the lecture 1, part 2, which I asked you to do. You remember that there were some vocabulary terms for when Earth goes around the sun. Earth has a closest approach, and Earth has a farthest approach from the sun. Its orbit is not a perfect circle. Do any of my students remember those vocabulary terms?
Is one of them a perihelion?
Correct. That's closest. Peri means next to. So perihelion is close to the sun. How about farthest from the sun?
Aphelion.
Aphelion, very good. Now, just like now I've exaggerated the squishiness of the of the Earth's orbit. It's actually very, very close to a circle, and it only varies by about 2%. Likewise, the moon's orbit is close to, but not quite a perfect circle. So for the case of the moon, when the moon is orbiting Earth, its closest approach to Earth is called perigee. That's closest to Earth. And this dot here represents the moon. When the moon is farthest from Earth, it's apogee. The fact that the moon and the sun vary by small amounts in their distance from Earth means that both the angular size of the moon and the angular size of the sun can change by tiny amounts over the course of a month and over the course of a year. And this leads to phenomenon that you might have heard about before, like the supermoon. When a full moon is at perigee, it's about 5% bigger or so than normal. When eclipses happen during apogee, you can sometimes get a lovely and magical type of an eclipse called an annular eclipse. Let's call up a photo of that. It's a very rare type of eclipse, and people make a cottage industry of taking cool astro photos of annular eclipses. Here's one in front of some clouds. Try to mix it up in case you did watch the lecture. And here you can see an eclipse that's taking place close to the time of apogee, and the angular size of the moon has shrunk down just a tiny little bit. You know, one of the things you guys are going to do with me in homework 2 is you're actually going to calculate the varying angular size of the sun and moon and find out the conditions for those eclipses using the formula that I taught you last time, the small angle formula. The small angle formula relates these 3 quantities together, and it looks a little something like this. Once again, this is all review, which is why I'm going quickly, okay? This is also a chance for you to ask me questions if you had any. The small angle formula tells you that the size or the diameter of your moon or planet is its angular size times the distance times 2 pi over 360 degrees. Very important formula. The most important thing to remember about this formula is that the angular size must be measured in degrees. John, I can hear your sighs, so we should probably mute you so I don't hear you like start to lose it, okay? Where are you? Where are you? That's okay. You can chime in at any time, John, but just unmute yourself and then you can into the camera and then, you know, maybe mute yourself again after that. Yeah. Say that, John.
I didn't expect you to hear that.
That's okay. I can literally, oh yeah, I need some iced tea, Jordan. Thank you. I can literally hear, the size. Oh my God, this guy's making me do math. What the fuck is going on here? Okay, hold on. Let me hide non-video participants. No trolls. Okay. Thank you, John. We'll try to keep muted unless you have something to share besides size for my help. Okay. The small angle formula. Now, I would do a sample problem with you, but guess what? I already did that in lecture 1, part 2, which you were supposed to watch. So maybe you should do that. Okay, take some notes. Now, I'm repeating myself here for good reason. This is wicked important stuff. Okay. I also want to repeat myself and say, if you think about it, what's up on the sky, right? We got the sun, we got the moon, we got stars. Anything else? What else is going on up in the sky?
Galaxies, planets.
Yes and yes. There are galaxies. Galaxies are really hard to see with the naked eye unless you live in a very dark sky. I was at a cool observatory in the mountains of Arizona outside of Tucson, and it was so dark there that I could actually see the Andromeda Galaxy with my naked eye.
What?
Kind of looks like a fuzz patch. But for the most part, you need telescopes to see galaxies. You can see some planets with the naked eye. Does anyone know how many planets can be seen with the naked eye? These are the 5 naked eye planets. Yeah, almost, Cole. You're one too many. Cole, it's actually 5 naked eye planets. And these are the planets of sort of classical antiquity, right? These are the planets that were worshipped by Greeks and Romans. They literally believed them to be their gods. And those planets are function F592, Mercury, Venus, Mars, Jupiter, and Saturn. Those planets can be seen with the naked eye, and they look much brighter than stars. They look like, well, they look like bright stars to your naked eye, but there's a few subtle differences. One of the classic rules that astronomers use is stars twinkle, but planets don't. And I can sort of demonstrate why with a couple of lovely photographs taken by a friend of mine. Where are those photos? I may have showed these during the lecture. I may not have. I don't think it hurts to repeat myself a little bit. Just a moment, guys. I have a couple of lovely photographs here. Here we go. Okay. Did you guys, let's ask the ones who watched. Did I show this to you guys last time? I did? Okay. So tell me what's going on here. Do we remember stuff? What did we learn? It's a view of the city of Providence with a few famous objects. This is the bright star Sirius. This will be in our lab today. Sirius is the brightest star in the sky. Doesn't look too bright in the photograph because they've exposed the image so that they'd capture the buildings, right? This is Venus and this is Jupiter. They are 2 of the brightest planets on our nighttime sky. Venus is actually brighter than Jupiter because it's usually closer to Earth, right? You can see in this photograph that both planets are brighter than the stars. So if you see a really, really bright object in your sky, there's a good chance it's a planet. Although Sirius can be very, very bright and easily mistaken for one. After the moon and after the sun, everything else on your sky is either a little tiny dot of a star or a little tiny dot of a planet. And for that reason, degrees are not a very good unit of angular measure in astronomy. You know, when you look at a degree, right? When you look at a degree as 1/360th of a circle, and I have an image of that here. The Greeks probably thought, okay, divide a circle up into 360 little pizza slices, and this is about as tiny an angle as you could possibly need. Except when, oops, sorry, that's not what I meant to do. When the circle becomes your sky is a 180-degree half of a circle, right? Then a degree is not a small angle. It's a big, clumsy, oafish angle. And even the moon and the sun are half of the width of your finger at arm's length. That's why astronomers had to invent smaller angles. Now, you're supposed to know about these already, but because we need them for our lecture today, I'll do a very fast review, just like I did with the small angle formula. And if you're sighing, John, it's because you didn't watch that fucking video. So go back and do it. That will make things less stressful, okay? All right. Let's do a quick review of our other angular units, okay? So in this class, we have 3 units for angle. We have the degree, and our definition of the degree is one circle is 360 degrees. You guys will remember that I told you that conversion factors play a big role in this class. I usually try to box my conversion factors, okay? And then we have 2 smaller units, which are the arc minute and the arc second. Now, I'm going quickly here because this is supposed to be review. 1 arc minute, okay, 1 arc minute is 1/60th of a degree. So my better definition is 1 degree contains 60 minutes of arc, where notice that I've used a single apostrophe to represent 1 minute of arc, okay? 1 arc second represented with double quotations is a 60th of an arc minute. So 1 arc minute contains 60 arc seconds. And these are your conversion factors that you should have written down in your notes, all right? Using them, we can use our dimensional analysis skills to convert between degrees, arc minutes, and arc seconds. And that's something I'll be expecting you to do now and for the rest of the class. That's kind of important. To help you understand what these things mean, I shared a slide with you trying to represent an arc minute and arc second. So here's a degree. We're zooming in on it with Adobe Photoshop. And then we're going to chop our 1 degree up into 60 more little slices of pizza, each of which is an arc minute. An arc minute is the equivalent of looking at a soccer ball from a half a mile away. Now try to imagine looking at a soccer ball from half a mile away. Do you think you could make out this, what is this, a pentagon pattern on the black and white objects? Ethan says no, he's doubting that. Ethan, if you could see the soccer ball, it would probably look like a little speck of gray fuzz. Probably the white and the black would kind of smear together. Obviously, your eye cannot see down to infinitesimally tiny little angles. And a big plot point in the history of astronomy lesson, which you'll get next week, is that the limit of human vision for a well-trained or a 20/20 eyeball, the limit of human vision is approximately 3 minutes of arc, okay? So any angle smaller than 3 minutes of arc is usually undistinguishable to you. And that means, as Cole mentioned with his nodding, the checkered pattern on a soccer ball would be difficult to resolve from half a mile away. Arc minutes are truly small, but arc seconds are even tinier. That's when we take an arc minute and we break it up into 60 more microscopic pizza wedges. An arc second is the equivalent of looking at a dime from 2.5 miles away. Obviously, your eyeball would be very hard pressed to even see the dime, much less make out the FDR or LBJ, whoever the hell that is. I always get it confused. I think it's FDR on the dime. If anyone is a coin enthusiast and wants to chime in here, please do. A star like Betelgeuse, the shoulder of Orion, subtends 55 milli-arcseconds, which means 0.055 arcseconds, microscopic angle. Planets like Jupiter and Venus, they have roughly a 1 arc minute angular size. So arc minutes are good for planets, arc seconds are good for stars. That's a sort of rule of thumb. Now, in the photograph that I showed you, you can see that both Jupiter and Venus in this photograph are unresolved objects. And that means from the camera's eyeball view, we're seeing them as microscopic dots. This is a brighter dot than that dot, but you can't really resolve their angular size because you can't see it as a disk. I should have had a lecture with you or a lesson with you where I said a resolved object is one that you can see as a disk. An unresolved object is one that appears as like a dot or a point source. In the follow-up image, using a small telescope or a telephoto lens, he has magnified the image, and now we can see Jupiter on the left as a resolved disk about 1 arc minute in angle, and you can see 1, 2, 3, 4 moons, those are the Galilean moons, as unresolved point sources nearby. In the lower right-hand corner, you see Venus. Venus is famous for going through a set of phases, just like the moon. And so we're seeing Venus in what looks to me to be a gibbous phase here. That's like the egg shape, okay? Yeah, Preston, talk to me, baby.
Hey, Professor. So when you were just describing how the alignment can be either closed or unclosed, are we going to be representing that with our just regular open and closed brackets, like from lecture 1 with the powers of 10?
Okay.
Or is that a further question kind of thing?
No, it's not a further question. It's just we're miscommunicating with each other, and
Okay.
I want to resolve that.
Okay.
Where is the open and closed brackets coming from? Like what?
Oh, in your sense of open and close alignment with looking at the stars from, it was your previous two slides.
Okay.
The one where there was a conjunction between one, where there was no conjunction between another. Is that going to be represented with our first lecture? Was what I was wondering.
Yeah, I think I did. It's been a while
Okay.
since I gave it, but let's do it again. So the thing that I had to tell you there, now you're getting confused. It's not open and closed. The term is resolved. I think that's what you're focusing on. Okay.
Mhm.
This is a thing from like a more advanced optics class. But at some point I realized in the process of teaching this course that this is a concept that's so important for astronomy, and it is not beyond you guys to understand it. Okay. Let's take this, Preston. This is a Frisbee from some submarine sandwich shop in East Providence that I like, okay? This is a resolved object to you because you can see the Frisbee through the camera, and you can see, like, if I put a little red dot at the top here on my Frisbee, you can see that the red dot is on the top and not on the bottom, and that means it's resolved. Now, if I made this Frisbee farther and farther and farther away from the camera, and I'm half tempted to do it as a demo, eventually there would come a part where the angular size for this Frisbee shrunk down so much that you wouldn't be able to distinguish the red dot from the sacks from the bottom. It would all just kind of turn into a microscopic point. And at that point, no pun intended, it would be an unresolved object. Let's take a quick note about this. Objects can be resolved or unresolved in your field of view, in your vision. Now, the way resolved versus unresolved looks will change depending on whether you're talking about a single object or a pair of objects. Let's draw both. If an object like the sun or the moon is resolved, you see it as a disk, okay? And that means you can distinguish with your eye or your telescope or your camera, the top is distinguishable from the bottom of the disk. When the angular size shrinks down to less than 3 minutes of arc in your eyeball's field of view, it becomes unresolved. Astronomers refer to that as a point source. It's a microscopic speck. You can get light from a point source. You know those little twinkling things in the sky you call stars? Those are all unresolved point sources. You can fucking see them because there's light coming down to your eyeballs, but you can't see the top of a star as distinguished from the bottom of the star. They're just dots of light, okay? They're pretty. Check them out sometime. Okay, now, if you want to talk about two objects, let's say you've got two objects that are almost point sources. Now, these are clearly resolved in the eye of the camera because most of you can see the top. At least on my screen, I can see the top from the bottom. But if they were so far away as to be point sources, you might be able to see two individual point sources. But if they keep a fixed distance from each other, as they got farther and farther away, they would look closer, and the angle between them would look smaller and smaller, and they would get closer and closer together. So when you're dealing, say, with a binary star system, sometimes resolved can mean that you see 2 point sources. Here, you're not resolving the stars, but you're resolving the binary system as 2 stars.
Okay. Understood.
When they get closer and closer together, the 2 binaries overlap, and then they become a single point source. Do you see what I mean?
Oh, okay. Absolutely. All right. Thank you, Professor. Yeah, I hadn't noticed that before, actually.
Okay. Yes. And you can try it yourself sometime, you know, like, well, it's nice if we have a big classroom. I can kind of tape 2 markers to a meter stick and try to run away from the class. It has various effects, but here on my camera, I'm kind of limited with the depth of view here. So, okay, so here, try a couple of examples. Here's my cat laser. Resolved or unresolved?
Resolved.
Well, this is a tricky one. It's actually just a point source, but it's kind of smeared out a bit on the camera's eye. But that's a dot. I mean, that's kind of a dot to me. I can see that on your thing, it looks like a disk, so that's fair, okay?
So would we describe point sources as different from spectrums of light being emitted? Like a cat laser, that's going to be just a point source because that's considered just a source of one point. Right?
It's considered a point source because it's a freaking dot. It's a little microscopic dot. Okay. Now, when you throw the word spectrum in, you're talking about something totally different, and you are going to be trained on what that means.
All right.
Spectrum is breaking light into its component wavelengths. We are nowhere ready for that yet. We will be eventually. Wait 2 or 3 weeks, and we'll be getting into spectrum. Okay. But for now, do not use that term. That's a machete you are not ready to wield yet, okay? Okay, so this is a dot. It's a point source. The marker that you see here is clearly a resolved object. You can see the top as distinguished from the bottom, and you can even make out some writing on it. You see what I'm saying?
I do.
Okay. All right.
Thank you, Professor.
All right. And keep them questions coming, Preston, because these dialogues are good for us. They help us learn. Okay. Degrees, arc minutes, arc seconds. That concludes my review of lecture 1, which some of you clearly want to go and watch. Now we get into some new stuff. Today, we're going to learn about the celestial sphere. We're going to learn about the local sky. We're going to learn about how objects move through our local sky. And yes, we're going to be using some angles and a little bit of geometry, okay? So let's begin with the thing that our lab is based on today. This is a model of the sky invented by the Greeks. The Greeks believed that Earth was the center of the universe, and that the planets and the sky sort of revolved around Earth. That's what it feels like if you're standing out in a field at night watching the sky rotate, okay? This might not be true, but it's a useful lie. Sometimes lies are more helpful than the truth. They help you to understand what's going on. Since we need to look at the sky from an Earth-based perspective, it actually might be helpful for us to get inside the Greeks' mindset because they were careful observers of the sky, more careful than we are today, all right? So let's start with this guy here, the celestial sphere. I want to identify 3 vocabulary points: North Celestial Pole, South Celestial Pole, and this ring here, the celestial equator. In fact, let's draw it on our board. Okay. The celestial sphere is a useful lie. The celestial sphere is a sphere of infinite radius, which means we're not going to be paying attention to how far away the objects are. We're just leaving that, so they're so far away that it's pointless to even think about it. A sphere of infinite radius on which stars, planets, sun, moon, and yes, galaxies and nebulae and things, on which all the things that you see in astronomy seem to rotate. And of course, stars rise in the east and set in the west. So they rotate from east to west. If we made a little model of it, we would draw our celestial sphere with a tiny little Earth in the center. We have some vocabulary points. We have the North, celestial pole, NCP, and that's sort of up here, right? Celestial pole. We have the projection of Earth's equator. Okay. We have the celestial equator. And then somewhere down here, we have the south celestial pole. Now, if I had to define these, oops, sorry, camera's not in a great position. South celestial pole. If I had to define these terms, and by the way, I'm going to be using these terms so much that I have acronyms or abbreviations. North celestial pole is NCP, celestial equator is CE, and south celestial pole is SCP. That's going to be very helpful for making diagrams and labels. See if you can follow along with that. So if I were to define the north celestial pole, I'd say something like the north celestial pole is the projection of Earth's north pole onto the sky. Projection of the north pole onto the sky. And I put it that way to remind you that not only is this a point in your mind in outer space, but it's a point on your local sky when you look out at night. The celestial equator is the projection of the equator onto the sky. And of course, the south celestial pole is the projection of the south pole. This marker is getting kicked, so I'm going to get rid of it. Sorry, my handwriting gets crappier the faster I go. I'll try to clean it up. Once you're done with these notes, I need to erase and take more. Ethan, it looks like you're writing. Is that correct? Can you give me a thumbs up when you're done?
Yeah, give me 1 second. I'm not him, but I'm writing too.
Yep, that's fine. I can sip some iced tea. There is a legendary astronomical object located at the North Celestial Pole. Do you know what it is?
Polaris?
That's right, the North Star Polaris. Let's take a peek. Let's pretend for a second that this is the astronomy class you thought you were going to take. You know, the one where like, here's a constellation, and this is the mythological history of it. Yeah, right. Stuff for chumps. Okay, but let's just pretend for a quick second that that's what we were doing. Okay, so I'll teach you some stuff about the stars. Here's a famous portion of a constellation. The Big Dipper might be known to you because it consists of a lot of bright stars. 83. The Big Dipper is an asterism. It's a portion of a constellation. The constellation is Ursa Major, the Big Bear. And these three stars are the tail of the bear. And the McDonald's fry catcher thing, that's the butt of the bear. But the rest of the constellation is huge, and it goes across your nighttime sky. Anyways, you guys know the Big Dipper because that's the part of the constellation that's really bright. The front two stars are called the pointer stars because you can use them to find Polaris, the North Star. You make a rough line through the sky and it kind of points towards a medium bright star. No, it's not the star over your head. That's not how that works, okay? Not unless you're Santa Claus, okay? Now, Polaris, the North Star, is actually part of the Little Dipper, Ursa Minor. But this is most likely not familiar to you because while I can see Polaris in my sky and I know where it is, it's not a particularly bright star or one that would just kind of pop out to the casual observer. In fact, from the observatory where I take students and open to the public, the Margaret Jacobi Observatory, which I hope you can come visit once we go back on campus, I can see Polaris with my naked eye. I can see this star Kochab, and I forgot what this one is, but I can see those three stars. But these stars, which I know are there, I cannot see in Warwick because of the light pollution. And that means you probably are not familiar with the Little Dipper. Matteo, talk to me.
I'm sorry, but could you move a little bit to the side? I just can't see the board. Okay, thank you.
Sure. Is it okay if I erase now, or are we still writing? I need some feedback here.
I'm still writing.
Okay. I see that X. I see that X. I think it was being shipped to FedEx. How we doing, guys? I'm gonna erase now.
Okay, I'm done.
All right. It's sometimes it's hard to figure. I want to go at the right speed for you guys. I don't want to waste time, but just keep talking to me. Okay. Now that you know about the celestial sphere, I need to tell you a rule that is not obvious to you. In fact, even though I just erased that section of notes, could you include this as part of that? Include this note as part of that last set of notes. You can always see exactly 1/2 of the celestial sphere on your local sky. Okay? You can always see 1/2 of the celestial sphere on your local sky. That is not an obvious point. To help understand, let's take a look at a slide that I've developed. Here we go, slide 49. Okay, imagine you're standing on Earth somewhere where this yellow arrow is. When you're standing in a nighttime field and you're looking up at stars, you tend to think of yourself as like a little dude surrounded by this kind of little dude sky. And you're used to thinking that the Earth is so big that there's no way you're seeing all of it or something. In fact, your little dude sky is actually kind of a big dude sky. It's actually all of the stuff that you see in green here. And the reason why your local sky encompasses 1/2 of the celestial sphere is because technically the celestial sphere is infinite in radius and Earth is microscopically small. You're used to thinking that because you can't see the North Pole from Rhode Island, that it would be weird to see the projection of the North Pole onto the sky. But to really draw this picture correct, what you would actually want to do is you'd want to draw the sky like this, right? This big infinite celestial sphere. And relative to this, Earth should be nothing more than a mote, a microscopic dot. I need another blue marker here. I like to use blue for Earth. Okay. So imagine instead drawing that same picture, this time with Earth as just a dot. If your head points in the direction of the red arrow, if you're located at some latitude, soon to be defined, your head might point in that direction towards the sky. And there's essentially no difference between the line through the center of Earth and the line through your feet. It's actually the same thing. So all of this stuff that you see here, that's all part of your local sky. As Earth spins in a 24-hour cycle, your head and the Earth keep rotating into different parts of the celestial sphere. You, of course, interpret it as stars rise in the east, that's your eastern horizon, and stars set in the west. So your horizon is rotating around the sky like this, you see? From your point of view, stars are coming up in the east and setting in the west. You tend to think of yourself as stationary, and that's a physics thing about reference frames. I don't know if I want to get into that just yet, but okay. In any case, your local sky, if you ignore buildings and trees, contains 1/2 of the celestial sphere always. Now that we've got that question. Yeah, Ethan, hit me.
It's not really a serious question, but it just has to go with this. Because you were saying, apart from buildings and stuff like that and trees, if you were in the middle of the ocean with nothing else around you, you could see half the world pretty much, like up in the sky. Like what the, not half the world, but
yes,
up in the
yes,
sky.
one of the things about talking right to each other is we have to use careful in our vocabulary. When you say world, this is what I'm thinking, right?
Yeah.
We're actually
But I
talking
mean, like-
about the sky. We're talking about
Yeah.
the world. Okay.
Where the
Oh.
sky looks over the earth.
In fact, yes, Ethan, that's what I was thinking. Places where you would really see a full expanse of the celestial sphere. Obviously, a ship at sea, and I don't know if we have any sailors or former sailors here. Ship at sea, you see the whole damn sky. In the desert, like if you're out in the deserts of Tucson, it's actually so strange. You know, I am a Rhode Islander like many of you, a native Rhode Islander. And I went to college out in Tucson, Arizona. And when you get out into the West and there are these big epic vistas, the sky is like this massive, awesome thing hovering over your head. It's like the whole dome of your local sky there. We are so not used to that in Rhode Island, and we don't even think about it because our environment is so cramped with hills and buildings and trees. It's all packed in. And as a native Rhode Islander, when you go out to the desert for the first time, like I was 18, and you just see these like epic expanses and vistas, it's not only beautiful and cool, but the sky is this big, friendly, intense thing right in your face. It's a cool experience to have. Certainly recommend if you ever do your Jack Kerouac post-college on the road trip, whatever, drive through the Southwest, eat some, El Pastor tacos and look out at the nighttime sky. Okay, you're going to thank me for it. Okay, now that we've done that, our next order of business is to come up with some vocabulary terms to describe our local sky. And I want to do a little Bob Ross moment with you guys here. And what I want to do is I want to make this. I want us to draw a model of our three-dimensional local sky so that we can come up with some vocabulary terms. Now, did any of you actually get a small plastic ruler like I suggested? All right, Daniel Cole. This is so handy to have, and it doesn't cost much. It costs like $1. If you don't have this, find like, you know, a box or something that you can use as a straight edge. Okay, let's make a 3D view of our local sky. I'll show you how I do it. Title this section of notes a 3D view of the local sky. The local sky is a buzzword in our astronomy class. Leave yourself some headroom. I'd recommend if you're doing this on your notebook paper, 10 centimeters would be a good reference line for you guys to start with, okay? So I'm gonna do a slightly bigger one because I have a whole board to work with here. So I'll do, I don't know, maybe for the purposes of note-taking, I'll do 50 centimeters today. So I'm going to do a 50 centimeter line. You guys do a fifth of that. You guys do 10 centimeters. I'm going to mark the midpoint of my line with a little dot here, okay? And here's an old school trick that you can use. If you want to draw a nice dome, if you made your line 10 centimeters, use a 5 centimeter radius, and you should be able to mark off some dots that will measure the height of your dome. So I'm going to go half up. You guys would do 5 centimeters up, and I'm going to put a dot there. But I can also, I can kind of go 5 centimeters out over here, over here. I'm just going to make a few dots that are all 5 centimeters away from my midpoint. And those are going to help me kind of connect the dots and make a pretty decent freehand dome, okay? So now that I've marked my radius as a bunch of dots, I can sort of connect them, and no kidding, here comes a nice, pretty decent semicircle, okay? Now, to make our drawing 3D, let's put a dash above and below the midpoint of our line, and let's connect the edges in a kind of oval, and this is going to make a sort of 3-dimensional ground for us. Good scale to be able to kind of draw this. Now, because I'm feeling artistic today, we're going to draw some grass in our field. We're not desert dwellers here in Rhode Island. We are grass dwellers. So we will draw some grass, okay? Now listen, it's very important for you guys when you make these drawings to decide what the 4 directions are going to be. And because I am a right-handed person, I always choose north to be my right side of the diagram. And I think we should all get in the habit of doing that for now. I'm going to put north on the right, put south on the left. That would make east into the plane of, or sort of into the camera view. That's east. And into the plane of the board would be west, okay? We can even draw a little observer dude who's standing in the middle of the field. There's your observer, okay? Let's go ahead and mark off some positions that have special vocabulary terms. These are called the fundamental positions of your local sky. I'll start by drawing a line right through the head of my observer, piercing the sky, and that's called the zenith. I'm going to mark it with a Z. And we'll put our vocabulary words down here. So the zenith, nice simple definitions, is the point overhead. Okay? Next up, I want a vocabulary term to describe the ring at the bottom of my local sky. That's called your horizon. The horizon is a 360-degree ring at the base of the local sky. The horizon, when most people, like, I don't know, someone on a ship thinks of the horizon as a point on the ocean, someone in the desert thinks of the horizon as a point on land. As astronomers, our concept of the horizon is a point on the sky. It's the last point where you can see stars rise or set. If I tell you that a star is on your western horizon, that means the star is somewhere along that side of the arc, okay? Let's draw a line pointing out to, pointing to the horizon. It's right there, okay? That's your zenith. That ring is your horizon. We also have a vocabulary term to describe an arc that runs from north to south through your zenith. And it's basically the kind of dome that we just drew in there. And that's called your meridian. Very important vocabulary term. The meridian is a semicircle or an arc that rises due north, reaches your zenith, and sets due south. Notice I've underlined north, zenith, and south. Those are the 3 key points. You're going to notice me doing that. Whenever I describe a trajectory through the sky, I always have 3 points. Where does it rise? How high does it reach? And where does it set? Okay. Now, let's assume for a moment that the local sky is a Rhode Islander's local sky. Should I be able to see the North Celestial Pole from Rhode Island? Yes, says Daniel. And that makes good sense to me too, because in Rhode Island, we are north of the equator. Anyone north of the equator should be able to see the North Celestial Pole in Polaris. By the way, I think I got, I don't know if I got sidetracked there, but Polaris, the North Star, is the tail of the Little Dipper here, right? So I think I did mention that actually. What was that, 34? Where was I? Okay. Let's go ahead and draw in the North Celestial Pole and the celestial equator into our diagram. So I usually use blue for the North Celestial Pole, just because I do. So I'll draw a line from the foot of my observer, and I'm going to draw it about halfway up the dome or so. It's something like that for us. This is our North Celestial Pole. And let's remind ourselves that Polaris should be on our sky. So I'll put a star here, and that's Polaris. Now, to draw in the celestial equator, this is takes a bit of skill. We want the celestial equator at all times to be 90 degrees to the north celestial pole. And what I'm going to do, I'm going to make a dash up here at a sort of 90-degree angle. And I'm going to attempt to draw a ring in. I have trouble with this. That's at all times 90 degrees to the north celestial pole line. I'm sort of, I should have hit due east there, but I'll just change due east. That's what I'll do. Cheat. And so those are also fundamental positions of the local sky. We have the north celestial pole, the NCP, and we have the celestial equator. And we can label that CE on our diagram. I know red doesn't come out quite as good on the camera, so. Keep track of time here. I don't want to screw this up. Ooh, damn it. Okay, I have a half an hour to do our 3 coordinates. This is going to be slightly unpleasant. I kind of need to give you our 3 coordinate systems so that we can do our lab today. And honestly, I can make it slow and pleasant, but I discovered it kind of doesn't matter. It's just confusing at first, and the more you kind of work with it, the easier it gets. So I'm going to try to keep the notes efficient, and I'm going to try to do these quickly. How are we feeling, guys? Can I erase? Or Ethan, Nina, Cole, we feeling okay about me erasing? Yep, I like those thumbs up. All right, erase. Okay, we're going to discuss 3 coordinate systems so that we can describe intelligently how stars rotate across our sky. And those 3 coordinate systems are going to be geographical coordinates, and that's to describe your location on Earth. It turns out where you are on Earth will affect what stars you see in the sky. People in the northern hemisphere at the North Pole see a different set of stars than someone at the South Pole. Then we're going to have a coordinate system for the sky called the horizon system. That's good when 2 observers are at the same place, like in the field together at the same telescope. So that's good for your local sky. And then a 3rd coordinate system, and this is the one that we need for our lab today. It's the confusingest of them. It's the equatorial system. And this is a set of global coordinates that stay fixed to the celestial sphere. So I'm going to call them global sky coordinates, meaning everyone on Earth uses the same set of coordinates for the objects. I'll talk more about them in turn. I have to do these a little bit more fast than you guys would like because we need them for our lab today. So hang on to your hats. We're going to go on for a sleigh ride here. Okay, geographical coordinates. I need to erase here. All right, I'm doing it. Geographical coordinates. We are going to use 2 angles. The angles are latitude and longitude. Let's get their definitions up and then we'll talk about it. Latitude is defined as the degrees north or south of the equator. Longitude is defined as the degrees east or west of the prime meridian. Okay. If you think about it, Earth is a sphere. And you're walking on a two-dimensional but curved surface. Because Earth spins, it has a natural symmetry. It spins on the north to south axis, and that kind of makes the equator a unique line on Earth. Our entire Earth can be divided into a northern and a southern hemisphere, and the equator is kind of a natural starting point to measure our angles. If we march up from the equator, that's degrees north. Down from the equator is degrees south, right? So for instance, as an example, if you take the North Pole, the North Pole has a latitude of 90 degrees north. You'll notice that for each latitude, you have to specify an angle and a direction for completeness. 90 degrees north, of course, is different than 90 degrees south. Longitudes are funny because longitudes run like tangerine slices. They slice north to south, but they measure east to west. There is no natural symmetry or starting point to where longitude should begin. So humans, in particular astronomers and geographers, they sort of got together and decided that they were going to define the 0th degree of longitude, or the so-called prime meridian, to be a line that runs right through the front door of the Royal Greenwich Observatory in Greenwich, England, just outside of London. And the prime meridian is a longitude line. You can see it here running right through the front door of the Royal Greenwich Observatory. You can visit the observatory and you can stand here with one foot in the Western Hemisphere and one in the Eastern Hemisphere, and you can take a little selfie, okay? In fact, one of my former students went there and they brought me a wonderful gift. I have my very own Prime Meridian pencil from the Prime Meridian gift shop, and feel free to send me, bring me treats back from your adventures abroad, okay? I don't have it here with me.
Oh, I'm sorry. Isn't that where like the time zone also starts? Like,
Okay, so actually timekeeping is a part of this week's lecture, and we're going to focus on it more on Wednesday. But what we could say is, because the Earth is spinning, it's always going to be daytime somewhere and nighttime somewhere. And then, as you're mentioning, we have the problem of where does the day begin? Where do you make midnight start? We don't do that at the prime meridian, actually. We do it at the backside, the opposite of the prime meridian. Does anyone know what that's called? What the opposite to the prime meridian is called?
The international date line?
That's right. Let's take a peek at that. International, sorry, I can't see my typing because your faces are in the way. International date line. It runs opposite to the prime meridian, and probably one of the reasons they made it go opposite to the prime meridian is it kind of avoids most of the major land masses. Obviously, it's going to be hard for your mailman if it's like Tuesday on one side of the street and Wednesday on the other side of the street. So you'll see that the international date line actually does a kind of little bumblebee dance around places like Fiji and Tonga to avoid that issue. So if you're like a businessman and you fly from, I don't know, Japan to California, you might cross the international date line and actually go back a day from Wednesday into Tuesday. That can happen to you. So it's not the prime meridian, it's the international date line where we start and define the day as the Earth rotates. Stay tuned for more on timekeeping on Wednesday's class. This stuff is obviously a prelude to that. What is the longitude of the North Pole? Let's take a peek at my slideshow. Anyone think they can guess the longitude of the North Pole? In fact, the longitude of the North Pole is undefined because all lines of longitude converge at the North Pole. In mathematics, we call such a point degenerate or multi-valued. Multiple longitudes pass at the North Pole, so it doesn't have a well-defined longitude. That's okay because a latitude of 90 degrees north is still a unique point. Now, for our homework this week, a good idea is to know the latitude and longitude of our fair city, Providence, Rhode Island. We have a latitude of 42 degrees north and a longitude of 71 degrees west. You'll notice I always specify north or south, east and west with my latitudes and longitudes. There could be exam questions that hinge on such things, okay? By the way, it's remarkable. These iPhones are really neat. You know, you just go to your Compass app if you have an iPhone. I don't know what the equivalent is in the Google phones, but I'm sure you got one. I have a Compass app and I can actually get a high precision estimate of my latitude and longitude. Now I haven't figured out how to really, I had trouble with my focus last week and I got it fixed at infinity and I don't want to change that. But if you look below your Compass app, I actually have my coordinates and I want someone to pull theirs out. Maybe you guys, I'm in downtown Providence, so we can see if you're in South County, we might be able to measure a difference. Here I am in downtown Providence, right? And it actually lists me as 41 degrees north. Actually, let me do it the proper way. 41 degrees, 49 arc minutes, and 23 arc seconds north. And then I'm 71 degrees west, 24 minutes of arc. This is a high precision measurement, 44 arc seconds west. I wonder if you guys are different than me by a few arc minutes or arc seconds. Ethan, what do you got? Where are you, Ethan?
I'm in Wakefield, Rhode Island.
Oh, that's perfect, because that's far away from me. So what's your numbers read?
41 degrees, 27. I don't remember the terminology.
That's
And
arc
3
minutes.
arc minutes and then 3 arc seconds.
So if you're, what did you say, 27 or 29?
41, 27, 3.
So you're more than 20 arc minutes separate from me, right? That's, we're still at the same longitude to within a degree, but not to within an arc minute, right? So arc minutes will span length of Rhode Island. And how about your longitude? We might be more vertically aligned, I don't know.
71, 29, 43.
Okay, so we're not too far. So you're in Wakefield, right? To be honest, I never really travel further south than Warwick, it's sad. I'm like, you know, like how Rhode Islanders don't like to leave Rhode Island? I'm a worse version of that. I don't leave downtown. So let's see, Rhode Island, if we call up a map here. And so you can see that Ethan and I are separated. Where the shit is Wakefield? I don't even know. Okay, hold on.
It's south Kingstown, so it's like near Gantet.
All right, so somewhere over here, right? So we're different enough in latitude. I'm doing the thing I said I wouldn't do, which is drag this shit out. So we're like maybe 20 or 22 arc minutes apart, right? But because Providence is somewhat vertically aligned, we're only 2 arc minutes off in longitude. Okay, so
I'm all the way down in like Charlestown.
what do you got? Who are you and what do you got?
It's Jay.
Oh, hey, Jay,
the
what's up?
one without a webcam.
Oh, right, yeah. Well, you ain't the only one.
Technical difficulties though. Mine's technical difficulties.
All right, yeah. You're here in spirit with us. You're a troll, but not by choice.
Yes. I'm 41 latitude and -71 longitude.
It's only interesting if you give me the arc minutes and arc seconds, right? Because we're obviously at the same latitude if you just do it to, like Rhode Island only spans about a degree at best, right?
Yeah. Hold on. I'm trying to figure out how to do all this. I hate my phone.
You just look at your
It's turned off.
Whatever. Okay,
Just
look.
turned off on me.
You know what? Even better. Let's not get lost in the weeds. That's as much as I'm going to say about latitude and longitude. Figure it out, okay? Let's move on to talk about the sky. Okay, next up, we're going to talk about the horizon system. It is a simple coordinate system used to find objects in your local sky. Good for local sky views. It uses altitude and it uses azimuth. Altitude is defined as degrees along. Sorry. Wow, I'm doing it dumb. Apologies. Altitude is defined as degrees above the horizon. And for completeness, I should include degrees above the nearest horizon. Azimuth is defined as degrees along the horizon, measured clockwise from north. Here I'd like to underline above and along, as those are key distinctions. Okay, let's take a peek. Did you guys get that down? To help you understand this, a diagram could help. Here's a dude standing in a local sky, and they're looking at a star. Unfortunately, north is at this kind of kooky, cockeyed angle, but all right, whatever. And let's say there's a black star here that we want to take notice of. What we would do first is we would swivel along the horizon until we're closest to that star. And it's real simple. It's just degrees up from the ground, okay? So this star is maybe, I don't know, 45 degrees up or something like that, maybe 30 or 40 degrees up from the horizon, all right? So altitude is degrees up. Now, to specify the azimuth, this is the point that marks azimuth, okay, because it's the point nearest on the horizon. We start north and we go clockwise all the way around until we get to the nearest horizon point. Now, assuming this is north, that's 0 degrees, right? So east would be a quarter turn over here. That's 90 degrees azimuth. And then south would be down here. That's 180 degrees. And west would be like 270 degrees. So I'm guessing this particular star has an azimuth of maybe 300 or 310 degrees. So 45 degrees would be its altitude, and 300 degrees would be its azimuth. That's how we do this, okay? Yeah, Matteo.
So I don't know if I'm pronouncing it right, but azimuth, would it be, it's just a point like the radius, and you go from north and then no? Okay.
I object to your term radius.
Okay.
These coordinates are angles, and you should write that down. These are angles. A radius is a length, right? We're talking angles, homie, not lengths. And the technical definitions, the words we use really matter here to not be confusing. The angles for altitude are just how many degrees up. So you find the star and you go degrees up. And you know what azimuth is kind of like? Azimuth is like direction. Why don't we do a couple of examples, okay? So let's talk about azimuth is basically the same as direction, but it's a more refined version of it. Where's the eraser here? There we go. It's the same as direction. So due north is 0 degrees. Due east is 90 degrees. Due south is 180 degrees. Due west is 270 degrees. Now, we could further refine this if we wanted to. We could say, okay, so northeast is halfway between 0 and 90. So northeast would be 45 degrees azimuth, okay? If you wanted to describe a point on your sky, let's talk about the zenith. The zenith has an altitude of 90 degrees because it's a 90-degree angle up from your horizon. Weirdly, the azimuth of your zenith is degenerate. It's undefined. And that's because at your zenith, at the top of the dome of the sky, every point on your horizon is equally distant from the zenith. So for instance, north, south, east, west, all of these locations, none of them are any closer to the zenith than any others. In fact, this is a thing from like a higher level of mathematics. There's a theorem that you can demonstrate that if you create a coordinate system, a two-dimensional coordinate system on a curved surface, there will always be 2 points that are degenerate or multi-valued. So the thing kind of breaks down a little bit. That's still okay because an altitude of 90 degrees is a unique altitude. It's straight up over your head. Now, for those that whoever asked the question, Mateo, I didn't mean to shoot you down so hard. It's just the way you were phrasing things, it almost didn't even make sense to me to say radius. So you might have been trying to talk, you might have understood what you were talking about, but I didn't. Now you might have been talking about the radius of this disk here, but I didn't think that was helpful. You know what I mean?
I was just looking at the green like thing as like a circle, and then like the red line from the out of circle to the center. That's just the radius. So I don't know, just my brain.
That's okay. That's okay. And sometimes talking about it helps these things. But remember, these are angles. If I'm doing azimuth, I start 0 degrees north and I swivel along the horizon until I get to my closest point. That's your azimuth. And then for my altitude, I start at the horizon and I go how many degrees up, okay? All right. The horizon system is a really nice coordinate system to use when you and your friend or your grandmother are out at a telescope together, because you can sort of tell someone how to find something if you're located with them in the same place in the sky. Let me show you a telescope that I get excited about when I fantasize late at night. I like to dream about the plane wave 1 meter telescope. I imagine some rich benefactor sort of, coming to my observatory and telling me how much I mean to them. And let's see if there's a YouTube of this thing slewing in the clean room. Oh, by the way, just so that you can understand what this is a gourmet research grade telescope. It's not too expensive. So if you have any rich uncles or something, feel free. And you'll notice that this telescope is one of the ones that uses something called an altitude azimuth mount. Okay. So here you are at the observatory. You're doing some cool astroscience. Let's see if we can find the videos here. Come on, just search. Oh yeah.
You just like order this and then just have it in your house.
Yeah, well, you got to call them. This is expensive enough where they send the technician to your site and they talk. Yeah. They actually talk to you for a little bit and then they show up there. But yeah, like they have videos of them installing it at local colleges and observatories. And it gets me a wee bit jealous, to be honest with you. Okay, so now the purpose of this video is to demonstrate how altitude and azimuth are used, say, in a telescope. So here they are slewing this in the clean room, and you can see the telescope is slewing around like the turret of a gun in azimuth, and then you'll see the thing go up and down in altitude. So there they were slewing in azimuth. This is azimuth slewing, and they should see it go up and down at some point. That's changing altitudes there. Okay, so why the horizon system is good is because it's just stupid and simple. And if you're at the telescope with your Grammy, you say, hey, Grammy, could you point the telescope at the Orion Nebula? And your Grammy, she's going to go, I don't know where the Orion Nebula is. You say, oh, it's easy, Grammy. You're going to point it azimuth due east, and then I want you to go to an altitude of 30 degrees. Pow, there's the Orion Nebula. But suppose Grammy's down in Pensacola, Florida, right? And you're up in Rhode Island. If you say, Grammy, could you go out to the 1 meter and, point at the Orion Nebula, collect some data for me? She says, well, where's the Orion Nebula? You say, well, it's 30 degrees for me, right? But is it going to be 30 degrees for someone in Florida? Probably not, because you're at a different latitude. Oh, snap. And now I'm thinking of another problem too. Shit, dog, the sky rotates. Remember that? Remember that the sky is like not static, but like stars are rising in the east and setting in the west? Let me show you where we're going with all this hideousness. During the night, the sky does not stay fixed. Go and check it out. Stars rise on your eastern horizon. They come up on these kind of circles and they set down the west. So stars do not maintain a fixed altitude or azimuth as they travel through your sky. And if you're located in Rhode Island, stars travel through our sky in a somewhat complex way. They rise in the east, they come up and they cross your meridian at the highest point in their journey, and then they set down in the west. You're going to start to notice that all those little vocab terms I used, I'm going to start using them now, and you're going to start getting confused, okay? What we need in addition to the horizon system is a third coordinate system. One that stays fixed to the celestial sphere itself. We need a kind of latitude and longitude, but for the sky, so that if me and my Grammy discover a new nebula, and I want to call it Grammy's Nebula, I can specify the fixed coordinates of that nebula, and every other scientist will know that, hands off, that's my Grammy's Nebula, and if you want to buy it from me, it's going to be $19.95, okay? So, as you know, some people, some unscrupulous sorts, pretend to sell stars to other people. And they tell you that if you pay $19.95, you can own a star. Do not fall for such shenanigans, okay? You do not own the star. Okay, what's that third coordinate system called? It's called the equatorial system. And no, you're not going to like it, okay? So let's.
I was going to say it, but.
What's that?
I was gonna say it, but then I got afraid. I was like, I don't want to get this wrong.
Yeah. I'm busted by 3 minutes, but I need this for the lab. So it's not going to be pretty. I'm going to slap down the definitions and we'll use it in lab. Okay. Sometimes it'd be like this. I took too much time. I had too much fun. Let's get our third coordinate system down and then we'll take a little pause. Okay. I think I took too much time with that review earlier. Our third coordinate system is called Equatorial Coordinates. And we use these equatorial coordinates for the global sky, okay? They are two coordinates. One is called declination, and the other is called right ascension. The abbreviation that astronomers use for these, for declination, we use DEC, okay? We call it the DEC. And for right ascension, we call it the RA, okay? Now, the way this works is declination is kind of like latitude for the sky. And right ascension is kind of like longitude for the sky. But there's a slight difference between longitudes and right ascensions. Declinations are kind of the same. We measure declination as the degrees of a star measured positive or negative from the celestial equator. That makes declination pretty much the same thing as latitude, just projected up onto the sky. Right ascension is going to be weird because it turns out that whereas we measured longitudes as degrees east or west of the prime meridian, here we're going to have two different differences. One, we're only going to measure in one direction, and two, we're not going to measure in degrees. We're going to measure in hours, which is nutty. And part of the reason why is that the nighttime sky is rotating. For instance, guys, suppose I took this ring and I put the ring projected on top of the prime meridian. During the course of a 24-hour day, Earth is going to spin counterclockwise on its axis, and the prime meridian will sweep along these different tangerine slices of the sky. So because Earth is moving with respect to the sky, it actually makes better sense not to use degrees, but to use hours. And here's why. There is a relationship between angle and time in astronomy. And it goes something like this. On a spinning Earth, you spin in 24 hours through a 360-degree circle, okay? So in astronomy, there's this weird conversion where 360 degrees is equal to 24 hours of sky rotation. And I want you to see what happens here. If you take your calculator and you divide 360 degrees by 24, you've probably never thought to do this before. Okay, I did something fucky. Hold on. 360 degrees divided by 24 hours. You get exactly the number 15. That's not a coincidence. The ancient Babylonians who invented the hour, they intentionally divided the sky up into equal parts. Remember, they loved the sexagesimal or 60 base system. So that means if you divide these two, 15 degrees equals 1 hour of sky rotation. For astronomers, there's this kind of weird conversion factor. 15 degrees is equal to an hour. When it comes to lines of longitude or celestial longitude, I can measure in degrees or in hours, and it turns out to be more useful to measure in hours, just more confusing to learn your first time around. I'm about to define right ascension, but could you guys at least write down this? 15 degrees equals 1 hour of sky rotation. Just jot that down somewhere in your notes. I promise you that'll be important. All right. To define right ascension, let's do this. Right ascension is the hours and minutes, if you care for it, measured eastward from the spring equinox. If you watched lecture 1, part 2, which you were supposed to, probably didn't, but you were supposed to, then you will remember that eastward means counterclockwise in space.
And west is clockwise.
Yes, sir. Yes, Lionel, if that was you. The spring equinox was also mentioned during that lecture, but in a slightly different context, okay? The spring equinox in this context is a point on the celestial sphere. It is a point where the celestial equator intersects the ecliptic, definition number 2 of the ecliptic. And it's right here. That's where the sun is going to be on March 21st. I would say more about this, but we're out of time, okay? Make sure you have those 2 notes. If you missed lecture 1, part 2, this stuff is going to be kind of confusing, but you could probably muscle through it. Okay, we're going to do lab now. We're going to do the first 2 pages of the Celestial Spheres lab. Ethan, question.
Can I go print that?
Yeah, I like to take about a 5, sometimes 10-minute pause before we start lab. We're a little behind, but is everyone okay with that? Everyone who's hanging out live? Okay. I'm going to
Professor,
pause. Priscilla.
I have to go to work, so will the recording be available?
Of course. That's why we do this recording. And I will have the recording up by 5 p.m. or so. It takes about an hour or 2 to process the video, and then it takes some time to upload it to YouTube. So
Okay,
probably by the time you get back from work, it'll be here. Jump to an hour and a half, and you should be able to watch the lab and do it. Sound good?
Okay. Thank you so much.
No probs. Thanks for being here while you could. Okay, guys, I'll stop. Don't let me forget to unpause the recording, or Priscilla's going to be in big trouble. Okay, so pause, 5-10-minute break. What time is it now? iPhone time, it's, oh my God, 1:11. By at least 1:20, we're starting, okay? See you in a few.
He's gone.
I believe your mic might be muted over there, Professor, also. But my question was, working with the azimuth, is that going to be a constant variable that we're going to be seeing like in equations, or is that going to be specific to which direction you're trying to locate a specific altitude from, seeing as though like being on
Whoa. Just slow your roll for a second.
Correct.
The azimuth can change depending on what
Correct.
star you're considering and what time of night. So
Okay.
yes, it does change. When you say it's a variable, like while we do a little algebra in this class, there's not going to be a ton of algebra, a little bit, but not too much. Just rather than think of it as a variable, think of it as a coordinate. But
Okay.
it will change from star to star. It will change from moment to moment. That was a question. I just thought I'd put it in the recording. I also want to pause the recording here on these notes. Hey, Cole, really great question, and I want to cover that in this recording. Cole made a mistake. He accidentally watched today's lecture, which was the first part of this video. What you guys were supposed to do is you were supposed to watch, well, this was Wednesday's class. This was lecture 0 and lecture 1, part 1, and lab 1. That's what you should have watched. But then I asked you to watch lecture 1, part 2, which was the first 1 hour and 30 minutes of this video. This video has lab 1 at the end, so you didn't need to watch lab 1 again. Then the homework was here, but the beginning of this video was today's lecture. So Cole got a double dose. But Cole, you need to go back and get the notes for this video. That's really important, okay?
Yeah, I'll do that after class.
Thank you, Cole. Thank you very much. And thank you for everyone else who I want. Cole, you probably are not the only person of all the students in 1010 who's done something like that. So this was worth talking to.
Yeah, I was sorry about that. I just got kind of confused.
I know. I did a confusing thing, but I'm hoping from here on out, it'll just be 1 lecture per week, lab on Mondays, homework on Wednesdays. That's what I'm trying to do in all this, okay? All right, see you in a little bit. Okay, welcome back, friends, to lab number 2. Today's lab is on using the equatorial coordinates that we just learned about to find famous stars on the celestial sphere. We're going to do a portion of this lab today. The pages that I suggested that you print out were page 1 and 2 from lab 2. So just to help the viewers at home who may not have been paying attention, understand that happens sometimes. You go to Blackboard, and on your class tab, we go to lab. We go to lab 2, celestial spheres. If you right click, you can print out the first 2 pages of this lab here. Okay, that's what I've done. We'll also be, for that person who had confusion earlier, we're going to be submitting lab 2. If you click on lab 2 celestial sphere, that's where we're going to take a picture at the end and submit to browse local files. Okay. Okay, let's see if I can go into share. Actually, before I activate this, because I only get 1 shot to do it, a couple of things that you guys would like to know about before we begin. Constellations are not simply stick figures on the sky. Constellations represent territories or areas on the sky. And this slide here, slide 57, demonstrates that. Orion is a famous constellation that you can identify by the red star Betelgeuse, and he's got shoulders and 3 stars in the belt. But what astronomers have done is they've marked off all of the celestial sphere into one of 88 constellations that are recognized by the International Astronomical Union. So if there was, say, a famous star or a galaxy located here, we would say that that is in the constellation of Orion, even though it's not within the stick figure, because this whole territory surrounding Orion is part of that constellation. Just like when you go to a map of the United States, you're always in one of the 50 states. At any point on the celestial sphere, you are always in one of the 88 constellations. And that matters for today's lab because we'll be piloting around this thing looking for famous stars and constellations. And you're going to notice that the stars are these white disks and their names are labeled in black, okay? The stick figures that make up the constellations are kind of like these these solid blue lines, like that solid blue line is part of the line of Cancer. You can see the name of the constellation is in blue. Stars are black, constellations are blue. But you'll notice if you look close, and it'll be better when you see the phone, that there are these dotted lines here. These are the boundaries between the different constellations. And so sometimes during this lab, we're going to find a coordinate, and we're going to try to figure out what star are we looking at and what constellation is it located. So that should be all we need to know there. Let's see if I can connect to the remote camera and then we can get moving here. Okay, so that's connecting. All right, and let me just go to my settings real quick, and I want to, I don't really use this phone except for this purpose. Where are the bloody, oh, there they are, settings, okay. And let me go to the display. Oh, auto lock is never, okay. I don't know. It seems to go dark from time to time. That must be in the power settings.
Probably either power or brightness, because occasionally my phone, which is an Android, tends to do that on me.
Oh yeah, I just want to keep it from shutting off the screen here. I guess it's not doing that. Okay. Okay, let's just assume it's not going to happen. Okay. So here are the things we want to do to start off. Remember to please do your labs in pencil. Put your name. I'll put my name up at the top.
I just have a question.
Yeah, sure.
If we don't have a printer available and I'm just writing this out on paper, do I take a picture of the paper later and submit it?
That's what you do no matter what. And don't forget that I told you, if you're doing this by hand, I expect you to make table 1. You better make it look good. Label table 1, take a ruler, make this, and I want to see all that stuff too, okay? Don't just write the answers. If you don't have a printer, you need to do more work with your pencil. But that is not beyond you, I hope it's not anyways, to make this table and put those values in. Do you understand me?
Are pens also acceptable if we don't have pencils?
I mean, I guess it's better than not turning in anything, but once you start screwing up and making mistakes and scratching shit out, it's going to look like garbage and it's going to piss me off. And if it gets to a point where I'm having trouble reading it and I'm going to get tired and angry and I'm just going to -2 and move on. And I don't think you want to. Or so you could piss me off. You can do that if you want to, or you could go to CVS and buy a $2 pack of pencils. Now, you don't have to do that right now. I'd rather have you watch the lab, but I'd certainly recommend you do that in the future, because every time I see pen, I get pissed off. And then when I see scratchy, 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 I get really pissed off. And at some point, I'm like, fuck this, -2. So don't tempt me, okay? Get a pencil, 20 cents. But I'd rather have you do it in pen than not at all. That's for sure. Oops. Okay. So it's also important, and I keep telling people over and over again, you got to tell me what section you're in. People keep sending me wacky emails. I don't know what section you're in. Oh man, I just remembered that I forgot to send the link to that person today. I hope, let me ask, someone emailed me today. Oh, bloody hell. Priscilla, did you join this party? Fudge. I think I might have missed Priscilla. Where was that link? Participants, invite, copy.
Wasn't she the lady who'd asked to have to go to work?
Was that her? I hope so. I tried to send the email.
I think she said she was going to miss the lab.
Okay, thank you. Thanks for helping me there. Okay, all right. So Priscilla
I'm
did.
not mistaken.
Yeah, okay, that makes me feel good. I'm happy. Oh no, 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 no. I just broke the thing with my. Okay, I'm sorry, guys. I'm doing it dumb here. Please tell me that I can reconnect. Sometimes if I, all right, good, it worked, great. Okay, lab section, we are AS1010. Now you might be in section 001 or 002. If you're in the night class, you're 101, okay, I don't know. Put whatever your section is. Also, great idea, lab number 2. That way we stay on track with each other, okay? So get all that stuff down. Now, what we see here in table 1 are the equatorial coordinates, the right ascension, and the declination of the 10 brightest stars in the nighttime sky. Our job is to use these coordinates, use the celestial sphere, and identify what star they're talking about and what constellation it's in. Now, I'm going to kind of go here. Let's see if you guys can see this. Let's orient ourselves on this celestial sphere here. And I'm going to try very hard not to break this because these are like $500 and they don't make them anymore. So I guess they're infinity dollars now. This is the celestial equator that I'm pointing to with my pencil. Let me see if I can studio here. See if I get some light on this thing. Okay. The celestial equator is where we measure declinations from, and we measure them positive or negative from the celestial equator. So going up to this horizontal black line, that's positive 10 degrees declination, positive 20 degrees dec, positive 30, positive 40, all the way up to Polaris, which is at positive 90, okay? The right ascensions slice north to south, and they measure kind of eastward along the celestial equator, and they're measured in hours. Let's go to 0 hours of right ascension, which is right here. So this is the 0 hour of right ascension. And we measure right ascensions eastwards or counterclockwise. So this is 1 hour of right ascension. This is 2 hours of right ascension. We can even get into the nitty gritty of minutes here. The big tick marks, that's 20 minutes, that's 40 minutes. And these little tick marks are each 4 minutes across, okay? So for instance, the star Alpheratz, which is in Pisces, to me, it looks like its declination is positive 10, positive 20, positive 29, maybe, right? And its right ascension is 0 hours and I don't know, maybe 4 or 5 minutes, something like that, okay? Let's find some stars. Our first star is 6 hours and 43 minutes, negative 17 degrees. So I'm going to rotate around till I get to 6 hours. 6 hours and 43 minutes would be 20 minutes, 40 minutes, that's 44, so we're getting close. But I'm going to start at the celestial equator. The declination is minus 17 degrees. So I'm 6 hours and 44 minutes, and I go down minus 10, minus 20, that's my star. Now, everything is kind of written backwards on this globe because you're supposed to look through it, but can you guys see what the star is?
Sirius.
Sirius, the dog star. And the constellation?
Canis Major.
Canis Major, the big dog. That's the brightest star in the sky, Sirius, the dog star, and Canis Major. All right, next up, 737 right ascension, positive 5 declination. So we're going to go to 7 hours. That's 7:20. That's 7:40. 4 minutes earlier would be 7 hours and 36 minutes. That's really close. So we should start here along this sort of longitude or this right ascension. Our declination is positive 5, so that's halfway up. And it looks like we have Procyon, and that's in Canis Minor.
Professor?
Yeah.
I had a question just about the right angle from hours to minutes and the declination of degrees. As far as counting them when doing the hours and minutes, is that going to be considered counting eastward because it's in a counterclockwise rotation, except for when it's positive and negative in declination, which would be just a north and south direction?
Yes, and this is Matteo. Matteo, be careful in how you use some of these jargons and terms. You want to be real careful. I mean, part of learning how to talk the talk is by trying and having me correct you at times. I find that you're mixing up a couple of different terms together. So I'm not sure where the right angle came in, but remember that lines,
Only because it was at 6 hours, which I figured was going to be 90 degrees as is. So I just put it at right angle. And then I started counting.
No. So listen, for right ascension, even though you could put it in degrees, do not even think like that.
Oh, okay.
Right ascension, you only think in hours. You don't don't convert it to degrees. You're asking for trouble.
All right.
For right ascensions, we measure along the tangerine slices, 0 hours, 1 hour, 2 hour, 3 hour. If you're halfway in between, it's 0 hours and 30 minutes. Yeah, I know that that's 15 degrees and I know that's 30 degrees, but don't you do that. Don't you dare do that, okay? However, declination is a totally separate coordinate. When you measure declination, you do use degrees, 0 degree, positive 10. Don't mix up declinations and right ascensions. They're separate from each other, okay?
So the right ascensions are intended to be read backwards, whereas the positive and negative degrees are intended to be represented as pluses and minuses.
That's right.
Cool.
And your backwards is actually my forwards, because I think in terms of space. So I think of things spinning counterclockwise. So to me, counterclockwise is forward. Weirdly enough, okay?
Okay. No, I understand. Thank you.
All right, but cool questions, Matteo. You keep them coming, but be careful with your terms. Okay, so next star, 2040, positive 45. Let's scroll all the way around back here. Okay. So here's 20 hours, and there's 21 hours. Once again, we're going counterclockwise or eastwards. 2040 this is 2020, and that's 2040. But I always start at the celestial equator. I like to measure along the celestial equator. I wish they'd almost printed these here on the celestial equator, but I think they were worried about it getting messed up because of the scene. 2040 is there. We are positive 45, so let's do plus 10, plus 20, plus 30, plus 40, and boom. There's halfway up, plus 45. The star is Deneb. The constellation is Cygnus the Swan. Deneb and Cygnus the Swan. 1948 plus 9. Here's 19, okay? 1940, 44, and 48. Each tick mark is 4 minutes. So that's roughly 1948. Plus 9. Oh, sorry. Wow, guys, I was actually at 1848, right? Did you see how I screwed up there? 1948 is here. 1920, 40, that's 1948, okay? Sorry. Between 19 and 20 is where I want to be. Plus 9 goes up here. The star is Altair. The constellation is Aquila, the eagle.
Was that a Q or G?
That's a Q, sorry.
Q.
Aquila. Next up, 513, positive 46. Actually, yeah, okay. 513 positive. Sorry, there's a hole. I gotta make sure I don't. Oh, there's the hole. Okay. 5:13. So this line here is 5 hours of right ascension. So 5:04, 5:08, 5:12, 5:16. So 5:13 should be maybe about there. 5:13 positive 46, positive 10, 20, 30, 40. That's positive 50. So halfway down is here. The star is Capella. And this constellation here is Auriga, the herdsman. Auriga is a herdsman who carries a goat on his back. Capella is the eye of the goat. Okay. Okay, so that's Capella, the eye of the goat in Auriga. Okay. 5:13, -8. That's easy. So here's 5. Once again, 5:13 is maybe, I don't know, at the third tick mark or so. -8 is all the way to -10. Now, if you look here, people get confused. Saiph is this star, and this star here is Rigel. Rigel is the foot of the constellation Orion. The bright blue foot of Orion is Rigel. This lab is really fun when you do it with a partner sort of in our lab room. So sorry, you guys, you know, I know everyone hates the COVID Zoom thing, but we try to have some fun here. You'll eventually get to do some labs with me, presumably, if this, was it February 14th we're supposed to go back? Is that right? Okay.
Yes, sir.
All right.
Okay. And how do we feel? Are we excited about going back in person? Is that stuff?
Oh yeah. Oh yeah.
Yeah.
I need to get
I'd
out.
rather it be in person.
Yeah, there's only much
Yeah.
sitting around in your bedroom that you can do before you. It's funny, going to school used to suck until you realize that staying home all the time kind of sucks too, right? So it's funny how that works. All
Well, I
right.
have to go on campus anyway for work, so it makes no difference whatsoever.
Oh, Daniel, yeah, I thought you might look familiar. So you work on campus, huh?
Yeah,
Where do you work?
I'm a student employee at Human Resources.
Very cool. Ooh, I like to have a friend in the saddle there. Okay. So you will be talking. I think one of your coworkers, Carolee, took this class a semester ago. Do you know Carolee? Is she?
Yes, Carolee is one of my coworkers. Yes.
Very cool. Tell her I say hi.
Will do.
Okay. Okay. So 1410 and positive 19 is our next guy here. Actually, if you guys are okay with this, let's just do something. Can we? This is going to confuse people. Can we jump to 8? Because I'm in the 5-hour range right now. That'll save some time. So 5 hours and 53 minutes, positive 7. So here's 5 hours, 40, 44, 48, 52. And positive 7 brings us up to this legendary star, Betelgeuse, the red shoulder of Orion. So that's number 8. Be careful here. I noticed that these numbers were all close to each other, so I kind of saved them. All right, let's go to 1410. Let's go back to 7 here.
I just had a quick question about number 3 for
Sure
the
thing.
name of the constellation.
Yeah.
Is that CYQNUS?
Oh, sorry, G. I realized I never noticed that I'm ambiguous there. That's Cygnus.
Okay,
Cygnus
cool.
is a swan. All right, here we go. All right. I gotta be careful about that hole there because that can destabilize this quite precarious lab situation here, not OSHA compliant, okay? All right, so 14 hours and 10 minutes, 4-8 is right about there. And then we're gonna do positive 19, positive 10, almost to positive 20. Ooh, it's Arcturus. Arcturus is in this cute little constellation, Bootes. It looks like booties, but it's Bootes, the herdsman, okay? So this is Arcturus in booties. It's Bootes because the second O actually has an umlaut. Not every day you get to make use of the umlaut, but you're welcome. Bootes. Uh, 1627 and negative 26, okay? Oh, do-do-do, do-do-do-do. Oh, I'm just being real careful with that hole here. I've learned the hard way. 1627. So here's 16. There's 20, 24, 28. So I should start about there. And then what are we doing here? Minus 26. Down 10. Down 20. Down 6 to Antares, which is anti-Mars. Now, Antares is in this constellation here, which is Scorpius. Antares is a red giant star, so it gets confused with Mars. That's why they call it anti-Mars. Scorpius. Okay, 1836, positive 39. Let's do this here. Okay, very carefully. 18, 20, 1840, that's 1836, 4 minutes early. And then we're going to go to positive 39. 10, positive 20, positive 30, almost to positive 40. We are at the star Vega. And Vega is in the constellation Lyra, the harp. Now, what's the purpose of all this? Well, there's a couple of different things. One is to kind of know some of the names of the fun stars and constellations above your head. The other is to kind of show you how we use the right ascension and declination as coordinates, and that these stars always maintain more or less fixed coordinates on the celestial sphere, okay? Yes, right ascension is measured in hours. That's a little funky at first, but you can get used to it. You just measure like a clock around the sky. Okay. I'm gonna have us do 2 more little sections here. I think we've got enough time to do that. I want to stop by 2. These are the 5 naked eye planets tonight. And we don't print the planets on the globe. Does anyone know why? Why print stars on the globe but not planets?
Aren't the planets also in rotation as well?
Yeah.
That's correct, Daniel. In fact, the planets wander with respect to the background stars. The Greek word planetos means wanderer. So planets wander. To find out where the planets are, we have to look up their coordinates in a table called an ephemeris. And that's what I was doing just before class here. Let's see if we can take these values down here. So maybe like, hold on, let me get my, oh, here's a little ruler. Let's see if we can take down their coordinates real quick. Can you guys see what I'm doing here? Hold on. Okay.
It's frozen.
It's,
okay, never mind.
Sorry, I'm just going to kind of make a little thing here where I can take down the right ascension and declination. We have to report the constellation that the planets are in tonight. So here's the RA and here's the deck. Sorry. Okay. So for Mercury, the right ascension is 2012. The deck is negative 16 degrees. Venus tonight is 1847. And negative 16 degrees. 1800 hours for Mars. And wow, everything's in the bottom half, negative 23 degrees. Jupiter is 2231. and -10 degrees. And then Saturn is 2109 and -17 degrees. Okay. So let's see if we can figure out what constellation Mercury would be in tonight. If we use this globe, and I want to warn you guys something about this globe. This globe, let me get a cue card here. Wow, I just happened to have
What's the declaration for Mars? -23. Okay.
These globes, in theory, need to be updated because the Earth exhibits a small wobble that causes the positions of stars to drift over very long periods of time. I'd like you guys to notice, I can't get my hand up there, never mind. Okay, so this globe was printed in 1967 by the Triponese Planetarium Company in Saginaw, Michigan. So we are now in 2021, right? So it's been about 40 years or so. Every 50 years, you have to make small adjustments to correct for the wobble of Earth. And I'll be talking about that precession in our upcoming classes. Okay, but anyways, let's presume this is a perfectly valid view of our nighttime sky. The constellation, at least in 1967, if Mercury is 2012 and -16, then we would go to 20 and 12 would be like over here. And -10, -20, -16 is there. Can you see what constellation Mercury would be in?
Capricornium?
Yeah, Capricornus. Venus is 1847 and -16. 1847 and -10, -16 is here. And it looks like it's actually in Sagittarius. $1,800 and that looks like positive, but it's actually supposed to be a negative there. Sorry. There was a little eraser mark. Sorry about that. That's -23. So 1,800 hours -10 -23. Do. Don't cross the dotted line. Ooh, Sagittarius. Mars and Venus are in conjunction. Jupiter, 2231 and -10. 2231 is about halfway through. There's the 22 line and there's the 23 line. So 2231 is here. And then -10 would bring us down to about there. This is the age of Aquarius. Aquarius. Oops, sorry. Sorry, guys, I'm trying to hold my cam steady here. This is a feat of dexterity to do this. Lastly, 2109 and -17. So 2109 is just a little past 21. And then -17, we go down 10, almost down to 20. Ooh, it's not in Sag. It's not in Aquarius. It's actually in Capricornus. We cannot cross a dotted blue line here, okay? So it's in Capricornus. So Saturn and Mercury are near each other. All during the last semester, both Jupiter and Saturn were visible at our observatory after dark. So students last semester got wonderful visions of both Saturn and Jupiter, which was really cool. I think they have since set. So unfortunately, when you guys visit my observatory, you will not get to see them. But if you wait about a year, they'll come around again. So
I have a quick question.
yeah.
Capricorn is the constellation Capricorn, right? Or are they two different ones?
Nope, it's the same thing.
Okay, because last time we did this lab in when I was in AS1020, Saturn was still in Capricorn.
Right. And so if you think about it, Ethan, that makes sense. Saturn is 10 astronomical units from the sun, right?
Yes.
So Saturn has a very, very long period around the sun. And that, I don't remember what it's maybe 29 years or about 30 years to go around the sun. So from last semester to this semester, whereas Mercury, Venus, and Mars have all jumped around quite a bit, Saturn hasn't moved that much because its so-called synodic period, well, it just doesn't move as fast across the sky. That's what I'm trying to say. Does that make sense, Ethan? If that was Ethan?
So you froze for a few seconds. What was that last sentence?
Oh, I said Saturn doesn't move as quickly across the sky. It's telling me my internet isn't stable. I'm sorry.
Okay.
Whatever. Okay, one last little bit for us to do here. In fact, if you actually look at the ephemeris tables that I grabbed this from, those are not the actual constellations that they're in. You'll see that tonight, if you use a current ephemeris, this corrects for the parent positions, that actually Venus and Mars are in Capricorn, Jupiter is in Pisces, and Saturn is Aquarius. First of all, you're going to notice that all of the planets, they're always in zodiacal constellations, right? In our previous lecture, we learned that the ecliptic is the zodiac, so that makes sense. The reason why the actual constellations are slightly different is because the moon exerts these gravitational torques on the Earth, and it causes Earth to go through this very long gyration called precession. And precession is a wobble that the Earth does that takes 26,000 years to complete. And that means it's a very, very slow precession, and it slowly changes the relative positions and coordinates of stars. You actually have to correct your star charts every 50 years for the precession of Earth. And we've drifted enough in roughly 50 years where the constellations have changed. These coordinates will not change. These are the right ascensions and declinations of 4 key points on the celestial sphere. You'll recognize this as the spring equinox, the summer solstice, the fall equinox, and the winter solstice. These are actually points on the celestial sphere. And the spring equinox, for instance, March 21st, that's where the celestial equator meets the ecliptic. The ecliptic, you will remember, is the path of the sun against the background stars. If you're feeling confused, that means you didn't watch lecture 1, part 2, okay? The ecliptic is the path of the sun against the background stars. And this nubby here actually moves the sun along the dates of the ecliptic. So the sun is kind of changing its position night after night. And like pin the tail on the donkey, it has a different position. Let's move it up to March 5, 10, 21, or 15, 20. That's March 21st, right about there, okay? You'll notice that on March 21st, the right ascension of the sun is 0 hours, but it's also on the celestial equator, so its declination is 0 degrees. So the right ascension of the sun on March 21st is 0 hours. We write it like this when we do right ascensions, and 0 degrees. Let's move the sun to June 21st. Here's June. June 5, June 10, June 15. What's the best way to look at here? That's roughly, actually June 21st should be this dot here. Let me use parallax to fix that problem. Okay. What's our declination? Here's the celestial equator, +10, +20, and a little bit more makes it about, oh, I don't know, +23.5, let's say. Just pick a random number. okay? Can you guys tell me the declination? I'm sorry, the declination is what we just did. I'm so stupid. Well, oh my gosh, guys, that's last night's whiskey talking right there. Okay, I apologize. We just did the declination, positive 23.5 degrees. I don't know why I didn't start with the rate ascension. That was real dumb. That's why whoever's using pen, I'm going to hate you later. Okay, prepare to be hated. All right. Can you guys tell me the right ascension of the sun on June 21st?
Six hours.
Very good. And let's write it 0600. September 21st. Let's rotate around the globe. Ooh, watch out for that hole. Sorry, guys. September 5, 10, 15, 20, and that's 20, that's 21st right there. That's the fall equinox. What is the declination here? Huh?
It looks 180.
No, 180 is the degrees along the ecliptic. Do not ignore that. I'm sorry, do not pay attention to that. Declination is your degrees plus or minus from the celestial equator.
0.
Sorry?
0.
That's right. It's on the celestial equator, so it's 0 degrees. Can you guys tell me the right ascension?
Would it be 12 hours?
That's right. You can see 11, 12, 13. It's 12 hours. Very good. We can talk about this at the start of next class. Remind me to do that if you can. December 21st.
Professor?
Yeah, sure.
If the declination of degrees for September 21st was 0 degrees, wouldn't that make it the autumnal equinox?
That's correct.
Isn't the autumnal equinox 2 days after?
Okay. We normally peg the fall equinox to be as close to the 21st as possible.
Okay.
Because there are not exactly 365 days in a year, it causes the fall equinox to drift by a day each year. So on one day, it'll be like the 20, sometimes it can even be the 19th. It'll be the 19th, then the 20th, then the 21st, then the 22nd, and sometimes even the 23rd. And then we have a leap year, and that will reset it. We try to keep it hovering. That's what the function of leap years are, is to keep it pegged to the 21st.
And that would be the reason to have arc seconds and minutes involved so that the entirety of it can be as accurate as possible.
In a way that helps, yeah, but really the issue is leap years. Leap years are, the problem is there's this inherent tension between time and astronomy. We base our clock, our whole timekeeping system is based on astronomy. The spin of Earth is a day. The orbit of Earth around the sun is a year. But these orbits don't fit into nice, neat, simple, repeatable things. They have little drifts over time that we have to correct for. Okay. And one of the things we're correcting for is the fact that there's not exactly 360.
Well, we can't round a day.
Yeah, exactly. Something like that. Okay. But we want to keep the spring equinox pegged to March 21st and likewise.
All right.
You're right.
Thank you. Okay. Well, I was just, I like double checked on that because I saw it for a second and I thought it was familiar. And then I thought it was unfamiliar. And then I was like, I should refamiliarize myself. So I was all over the place for a second.
That's okay. That's cool.
Thank you.
Let's do December 21st next, which is the putative fall winter solstice. Okay.
That's my birthday.
So, is that your birthday?
Yeah, I just want to put that out there.
All right, winter solstice, baby. I love it. Let's see here. I'm getting lost in the sauce. All right, so here's December. Here's December 5, 10, 20, 25. There's the 21st right there. That's sort of how we're supposed to view it, okay? Now, unfortunately, this ball of the sun doesn't quite match up with the path of the ecliptic, because whatever little kid was building this in the sweatshop didn't, he didn't get it sort of angled right here. But the December 21st is supposed to be right about there. So it's the declination is -10, -20, and a little bit extra is -23.5. And the right ascension is up here, is 18 hours. It's on this line of right ascension. I guess then there's the question of today, right? So today is 1/24/2022. Let's just do 1/24, okay? So that's January 24th. We're just past the solstice. If January 24th is right about there, I'd say the declination of the sun is about -9 degrees today. And the right ascension on the 24th, let's see here. If that's the 20th and that's the 21st, we're pretty close to this tick mark. So that's 20 hours and 20 minutes. Nice, 2020. Okay, there's one last thing that I want to do before we end lab today. Let me get an eraser here because I didn't think about this. As you know, the worshipers of astrology believe that the location of the sun against the background stars on your B-day will determine your personality type. But one thing that the smokers of astrology don't understand is that those zodiac signs that they give you in your CoStar app or on the internet or whatever, those signs were based on a book written by the Arab Greek astronomer Ptolemy in the year 50 AD, 2,000 years ago or so. And the position of the sun 2,000 years ago is not the same as the position of the sun today, because the moon has been causing Earth to precess or wobble on its axis. Okay, it wobbles every 26,000 years, but 2,000 years is enough time where it's caused some serious drift. So for instance, if you think you're born in December 21st and you're Sagittarius, oftentimes it turns out that the sun wasn't actually in Sagittarius in your birthday. Now, who was the dude out there who said that his birthday was December 21st?
I am Ethan Brown.
Ethan, okay. Ethan, here's what I want you to do, and here's what I want everyone to do. Let me erase this. In the little space down here below, I want you guys to do this. So first, I want you to list your B-day, okay, as a month slash, as a month slash day. So believe it or not, my B-day is 4/20. Okay, so that's my birthday.
I'm 4/29.
All right,
Nice.
cool. Ethan would put, Ethan Brown, because there's two Ethans, I realize now. Ethan Brown would put 12/21. And then there's your your fake sign, or I don't even know if I want to say fake and real, because none of it's fucking real. But
So you're telling me I'm not a Leo?
well, let's find out. Okay. So there's what your CoStar says. I love to pick on CoStar. And then there's the real position of the sun.
This could get controversial real quick.
Yep. Okay. So for instance, well, mine's kind of weird because I'm supposed to be like a Taurus, I think, right? But if we look up the position of the sun, it wasn't in Taurus anymore. Let's start with Ethan, because I'd rather talk about you guys than me. Ethan, yours is supposed to be 12/21. And what's your CoStar, your fake sign supposed to be? The one they tell you. You know?
I think it's a Sagittarius.
Probably.
I don't know.
Okay.
Someone's saying Capricorn. I have no idea.
Let's see what.
If you're December 21st, I'm not. Never mind. I'm not gonna get into this. Never mind.
All right, so like if we just looked up someone's zodiac sign, right? So if we do December 21st zodiac, I'm sure the one they'll tell you, it's Sagittarius, right?
Yeah.
Okay, so now let's go ahead and let's look up our globe to see what's up, okay? Let's go to December 21st. We were just there. January, December 21st is right here. Wow, fucking hell. Okay, so actually, if you look, you are still in the constellation Sagittarius. One of the reasons you still end up, if you guys notice, Sagittarius, the boundaries start here, but they end over here. That's a lot of right ascension span. So usually it drifts back by about a month or so. I thought it was going to kick you into the next one, but I guess December 21st, lamely enough, is still a Sagittarius. And that happens sometimes. So Ethan, you suck, okay? You're proving my point. Okay, let's try Daniel. Daniel, what's your B-Day?
June 19th. So popularly, that would mean I'm a Gemini.
Okay, so if you're June 19th, you're supposed to be a Gemini. Let's go to June 19th and see what's up. All right. Okay, if we do enough of these birthdays, people watching later will get a sense of this too. So here's June. We got to be careful. Oh, wait, so that's July. Here's June 19th. So there's June 20th. There's June 15th. Do you see the boundary of the constellation? Right there. Okay, so what constellation are you in, Daniel? You are in, don't cross the dotted blue line here. Well, I can't be looking through my camera. I have to look over here. Oh yeah, June 19th. So you're actually in Taurus. You are no longer a Gemini. You are now a Taurus, okay? And that's how it goes with most people. Some people still keep the same sign because of the drift. Cole, what's your birthday?
December 2nd, so I'm a Sag.
Okay, let's find out if you're still a Sagittarius. So let's go around to December 2nd, okay? Okay. December 2nd is here, okay? And you will notice that you are actually no longer in Sagittarius, because if this is Sagittarius, this is the constellation here, the boundary ends right about there, right around December 18th. You, Cole, are now a part of something very special. If you follow along up to here, you are now a part of the 13th zodiac sign, Ophiuchus.
I feel my personality changing already.
Yeah, Ophiuchus, you are the 13th zodiac sign. You must be very special. How about William Russell? What about you, Will?
My birthday is July 31st.
And what are you supposed to be?
I'm supposed to be a Leo.
Okay.
My birthday's next to yours, August 1st.
So let's go to let's go to July 31st. There's July 20th, 25, July 30, July 31st. What constellation was the sun in when you were born? Will.
Oh my God, it's a Cancer.
Sorry, bud. You're a Cancer now. Jacob, what's your birthday?
No.
Jacob?
Didn't realize my mic was dead on my headphones. July 5th.
July 5th. And what are you supposed to be?
A Cancer.
All right. June, July 5th. Oh, weird. You actually still are a Cancer. So, all right, so be it. Nina, what's your B-Day?
May 7th,
And what are you supposed to be?
a Taurus.
Okay, so let's go over to May 7th. There's May. There's 7, okay? Now the boundary for Taurus is actually here. So you're not in Taurus. The sun was actually in Aries on your birthday. So sorry, you're not a Taurus anymore. Now, the point is, you know, you can believe whatever you want. If you want to believe the earth is flat, if you want to believe that 5G equals coronavirus or whatever the fuck people do these days, you are free to be an insane person. No one can really stop you from being insane. But your sign that you've been told is your sign is probably not. Oh, sorry, I forgot Lionel too. Lionel, we want to get you in the action. What's your B-day, buddy?
10/11.
And if it's October 11th, what are you supposed to be?
Libra.
Okay, so October 11th actually puts you in Virgo. So sorry.
Oh, hell no.
You
Wait, I want to be in
know.
on this action. I want to be in on this action. Yeah,
Okay, come
include
on.
me in it.
Yeah.
April 29th,
And what are you supposed to be?
Taurus.
Eddie.
Okay. So let's go around to April 29. Sorry, bro. You're Aries now.
Everything I know is a lie. This is a
Yeah.
national tragedy.
Can
Well-
we do February 11th?
Yeah. What's February 11th supposed to be?
An Aquarius.
Let's find out here. Where are we? February 11th.
I'm not a Virgo.
Oh,
No.
here, check this out. February 11th is Capricorn.
Oh my
Sorry.
gosh.
What does it
Like
mean?
in this class, but not anymore.
What does it mean if your sun sign is not where the sun was on your birthday? That's pretty fucked up, right? Like your sun sign is supposed to be your Aries because the sun is in Aries in your birthday. But for the greatest number of you, with a few exceptions, the sun has drifted out of your constellation because of precession. In other words, unless you were born in 50 AD, okay, and cryogenically frozen or something, if you were not born in 50 AD, and in 2000 years, the sun has drifted you, maybe those co-star kids ought to update their fucking star charts. Maybe it shows you how little they don't really know what they're talking about, okay?
Excuse me, Professor.
Yeah.
With the whole sun being off of a specific mark when it comes to the astrological sign or astronomical sign, sorry, then would it really go to show that it would have been the sun that was disaligned, or would it have been the moon that's disaligned on the reverse axis of that because it's not in?
Oh, wait, slow your damned roll. You're doing two things at once here.
It's the one idea of astronomy.
No. There is no, wouldn't it kind of sort of be misaligned? The Earth is where it is, and the sun is where it is, and the stars are where they are at any one given instant. And 3 points kind of make a line here, right? Actually, 2 points make a line, but in this case, it's about Earth isn't really a point. The sky has the sun and the stars in the background. Let's go to function F561 so everyone can understand. Preston, do you agree that let's just start with some things we can agree upon. Do you agree that Earth goes around the sun? Yes or no? Preston?
That would be a yes.
Oh, okay. So then do you agree that as today is a certain day, that the Earth has to be in some particular point along this circle, which we call the ecliptic?
In
The
orbit.
Earth, right. And that means now the sun is also somewhere along the ecliptic. It's right here.
Orbiting.
And that means there are stars behind the sun, and the sun is in some particular constellation today. If we want to know exactly which constellation it's in, we can go to this website called ephemeris.com. I usually just type sun to Sedna.
Unless uncorrelated, which is why I was asking, would it be the
Wait.
sun or the moon?
I don't understand what you mean by unless uncorrelated. What is being correlated here? What's being correlated is the sun and the stars. The sun is in one spot right now, and the stars
So
are.
if it were uncorrelated, wouldn't that make it the sun, or would that make it the moon?
The moon doesn't. It's called your sun sign because it's the sun. The moon's got nothing to do with it. Now,
I guess,
yes,
no, the moon is supposed to be like the reciprocal of where your sun is on the reverse end of that, I guess, in some form of how they're
dude, and
supposed to teach it.
fucking Mercury's in Gatorade, and Aquarius is the 7th house.
No, but in legitimacy.
No, in legitimacy, that the moon and the sun's orbit are not related to each other. Not really at all.
Not what you just showed me in your PowerPoint, though. That's why I was asking. If it was
Bro,
uncorrelated.
the moon doesn't appear in this PowerPoint. Where do you see the moon in this picture? I don't see the moon anywhere in this photo. What you just said is false.
Where your sun is, the opposite is the moon.
Hell no. Dude, we're going to do the moon tomorrow and then Wednesday and the next day. The moon.
By astronomy. That's why it's uncorrelated. That's why I was asking if is it the sun that is telling these people that their signs are different from their
Yes,
actual
that's the
position
sun
in
sign. The moon is, you have some false ideas. One of your ideas, if I'm understanding you, is you think the moon is always opposite the sun. That is 1000% false.
That's your idea.
You're the one who brought up the moon, not me.
I said, would it be uncorrelated to the moon or the sun? It was one question, sir.
Would it be uncorrelated to the moon or the sun?
Because their actual position is different from their co-star.
The answer to your question is the moon has nothing to do with your sun sign. Your sun sign, as far as I understand it, is what constellation the sun is in.
That's
now,
what
yes,
I was wondering.
astrologers.
I didn't know how one thing backwards could tell it like forward a whole different answer. That's why I was like, I'm not all too sure about it. It was like kind of an illegitimate discussion, I guess, for the sense of what we're actually learning, though it still sat in my head. So I figured.
Okay, and so what I think is going on is the co-star people do give you a moon sign and all that. They have like what constellation your moon is in, but that's a separate thing. Even for astrologers, the sun sign is one thing and the constellation the moon is in another. And if you watch the orbit of the sun and the moon, they're complex. The moon's orbit is roughly a month. The sun's orbit is roughly a year. So they're changing in a dynamic way. I wasn't including the moon in any of this discussion, just the sun, just your sun sign. That's what people, when you're out drinking at the bar.
I was trying to visualize it in linearity, but I wasn't really sure exactly how to go over and try to apply that to what we're talking about.
It's not linear. It's 3D. It's very complex. Okay. Anyways, we got lost in the sauce there. We are done with lab number 2. Yay. Time to submit. You will submit a photograph of this page and a photograph of this page to lab number 2. Okay. And you will submit it. You will submit it here. You will submit it under Lab Assignment 2, Celestial Sphere. Click on that, and then browse local files and upload your picture. Okay. And I look forward to getting that lab from you. We will see each other on Wednesday. I'll send out a link around 11:30. And we will do the second part of this lecture, and we will do homework number 2. By now, you should have turned in lab 1 and homework 1. I didn't get to finish grading them last night. I'm gonna finish them today. Please get them in ASAP. If you didn't watch that other video, you can find the other video in the announcements section. This was, once again, I'm just saying this because sometimes things need to get repeated, okay? This is the video in the announcement section. This is the video that we did on Wednesday. That's lecture 0, lecture 1, part 1, and lab 1. This is the video you were supposed to watch the first hour and a half of that for lecture 1. Oops, sorry, this all just shifted here. For lecture 1, part 2. Sorry, there's too many damned windows and things here. I'm sucking. Okay. This here is lecture 1, part 2. That's what you should have watched on your own. And then this was homework 1 from last time. So presumably most of you have already done this, but if you haven't, you owe that to me, okay? This video will be posted at 5 p.m. Yes, Daniel.
All right, just a question. From when I submitted homework 1, I submitted 2 images, 1 image per page. Is that okay?
That is okay, as long as they're both under the same submission. And then make sure whoever submitted their homework and lab together, please separate them, okay? I allow multiple submissions for this reason, but yes, it's okay if your homework or your lab is multiple pages. That's okay, Daniel. Anything else, guys? Cole.
Does it have to be like a JPEG when we turn it in, or like is like
sometimes
one of
iPhones
those-
do like an HEIC. Put it this way, Cole. If
Oh,
I
that's
can,
what I uploaded in, so that's perfect.
and if I can see it, I'll grade it. So Cole, if you want, we could even kind of, what section are you in, Cole?
1010-001.
Okay, so here you are. So let's see, Cole Williamson. Can I do this? Oh, it might not show you for, oh, okay, it does. If I can see it, I can grade it. And yeah, Cole, looks cool. Oh, I can see lab 1 anyway, so presumably I'll see the others, okay?
Sweet, thank you.
All right, guys, I'm a phone call away or an email away if you need me for anything. If not, I'll see you Wednesday for lecture 2, part 2, and homework 2. Peace.
See you then. Have
a good day.
Bye.
Thank you, Professor. Have a good
Thank
rest
you.
of your day.
Sorry, I gotta end this.